Section 8.7 Power Series. In this section, we shall examine the properties of power series and shall find that under reasonable conditions, they can be differentiated or integrated term by term. An infinite series of the form sigma k equals 0 to infinity of ak multiplied by x minus c to the power of k is called a power series centered at C. We can also say that it is a power series in x minus c because it contains the powers of x minus c. The numbers ak are the coefficients of the power series. It can be expressed as a0 plus a1 multiplied by x minus c plus a2 x minus c squared plus a3 x minus c cubed plus etc. If c equals 0, the series has the form a0 plus a1x plus a2x squared plus a3x cubed plus etc. Please notice that a power series is a function. It may converge or diverge depending on the value of x. A power series in x may be considered as an extension of a polynomial in x. We consider the power series sigma k from 0 to infinity of x to the power of k. For a specific value of x, this is a geometric series. As we have known, the condition for the convergence of geometric series is that the absolute value of x is less than 1. Under that condition, it has a sum which is 1 divided by 1 minus x. When x changes, 1 divided by 1 minus x becomes a function of x. So, the sum of the given series is the function 1 divided by 1 minus x. An important question for a power series is that for what values of x does a given power series converge? The following example illustrates the method for solving such problems. Consider the power series sigma k from 0 to infinity 3 divided by 2 to the power of k multiplied by k, then multiplied by x minus 5 to the power of k. This series is centered at 5. We use the generalized ratio test. We take the limit of the ratio of the kth term to the kth term and take the absolute value. Simplify the common term, we get k multiplied by the absolute value of x minus 5 divided by 2 multiplied by k plus 1. The limit of k divided by k plus 1 is 1, so the limit is the absolute value of x minus 5 divided by 2. The generalized ratio test tells us that this series converges absolutely when the absolute value of x minus 5 divided by 2 is less than 1. It implies that the absolute value of x minus 5 is less than 2. Now we will use algebra to solve the inequality. The absolute value of x minus 5 is less than 2. There are two cases. If x minus 5 is positive, then the absolute value of x minus 5 is itself. Solving x minus 5 less than 2, we get x less than 7. If x minus 5 is negative, then the absolute value of x minus 5 is the opposite of x minus 5. Multiplying both sides by minus 1 and the inequality reverses, we get x greater than 3. That is another way to solve the inequality. The absolute value of x minus 5 is less than 2. We can use geometry. Remember that the absolute value of x minus 5 is the distance from x to 5. Plot 5 in the number axis. We find 2 points on the left and on the right of 5 that have the distance to 5 equal to 2. They are 3 and 7. So, the points whose distance to 5 is less than 2 lie between 3 and 7. The distance from 3 to 7 is 4. A half of this distance is called the radius of convergence. The ratio test tells us that the given series converge absolutely when x is greater than 3 and less than 7. But it tells us nothing at the endpoints 3 and 7, so we must check them separately. When x equals 7, the series becomes sigma k equals 0 to infinity of 3 divided by 2 to the power of k divided by k multiplied by 7 minus 5 to the power of k, which equals to sigma of 3 divided by 2 to the power of k divided by k multiplied by 2 to the power of k. Reducing 2 to the power of k yields sigma of 3 divided by k. This is a p-series with p equals 1, so it diverges. When x equals 3, the series becomes sigma of 3 divided by 2 to the power of k divided by k multiplied by 3 minus 5 to the power of k, which equals to sigma of 3 divided by 2 to the power of k divided by k multiplied by minus 2 to the power of k. Reducing 2 to the power of k yields sigma of 3 divided by k multiplied by minus 1 to the power of k. This is an alternating series. 3 divided by k is decreasing and converges to 0. So, it converges by the alternating series test. Summarizing what we have discussed so far, the series converges for x greater than or equal to 3 and less than 7. The radius of convergence is 2. We consider another example. Find the values of x for which the series sigma k to the power of k multiplied by x minus 2 to the power of k converge. Since the coefficient is also the kth power, the generalized root test is great for this case. We take the limit of the kth root of the absolute value of k to the power of k multiplied by x minus 2 to the power of k when k tends to infinity. Taking root yield k multiplied by the absolute value of x minus 2. When k tends to infinity, this limit equals infinity unless x equals 2. So the series diverges. When x equals 2, the limit is 0. So the series converges only at x equals 2. The radius of convergence is 0. Next, we find the values of x for which the series sigma x to the power of k divided by k factorial. Since the general term involves the factorial, we try generalized ratio test this time. We take the limit of the absolute value of x to the power of k plus 1 divided by k plus 1 factorial multiplied by k factorial divided by x to the power of k. Reducing the common terms gives lim when k tends to infinity of absolute value of x divided by k plus 1. This limit is 0 for every value of x. So, the series converges no matter what x is. The radius of convergence is infinity. The interval of convergence is the entire real line. The following theorem tells us about the convergence of a power series. Exactly one of these possibilities occurs. 1. It converges only at x equals c. 2. It converges at every number x. 3. There is a number r greater than 0, so that a. It converges absolutely if the absolute value of x minus c is less than r. b. It diverges if the absolute value of x minus c is greater than r. The set of values for which a series converges is called the convergence set for the series. From this theorem, We know it is always an interval if one considers a point and the entire real line as intervals. The examples we have considered previously show each case of these possibilities. The following example illustrates more clearly the theorem. Suppose sigma ak multiplied by x minus 3 to the power of k converge at x equals 8. Does it converge at x equals 6? To answer this, we draw the convergence set of this series. The series is centered at 3. It converges at 8. So for all values of x between 3 and 8, it converges. Since 6 lies between 3 and 8, it converges at 6. Does it converge at x equals minus 1? We find another number on the left of 3 which has the same distance to 3 as 8. This number is minus 2. So the series converges for all x greater than minus 2 and less than 8. Since minus 1 lies in this interval, it converges at 1. Does it converge at x equals minus 2? The theorem does not tell us about the endpoints, so we are not sure about this. Does it converge at x equals 9? Since 9 lies outside the interval from minus 2 to 8, we have no information to give a certain conclusion. A power series can be thought of as a function defined on its interval of convergence. It is reasonable to ask if this function is differentiable or integrable, and if so, what are its derivative and integral. If we regard a power series as an infinite polynomial, we would expect to be able to differentiate and integrate it term by term. The following theorem shows that this procedure is valid on the interval of convergence. Given the power series sigma of ak multiplied by x minus a to the power of k, it can be differentiated term by term to obtain the derivative as sigma of k multiplied by ak multiplied by x minus k to the power of k minus 1. It can also be integrated term by term. The integral is sigma of ak divided by k plus 1 multiplied by x minus a to the power of k plus 1 plus c. These procedures are valid on the interval of convergence of the original series. For example, differentiate the power series sigma 1 divided by k factorial multiplied by x to the power of k. It can be shown that this series converges for all x. Differentiating term by term gives 1 divided by k factorial multiplied by k multiplied by x to the power of k minus 1. The initial series can be expressed as 1 plus x plus 1 half x squared plus 1/6 x cubed plus 1/24 x to the 4th plus etc. After differentiating, the result is 0 plus 1 plus x plus 1 half x squared plus 1/6 x cubed plus etc. The derivative is the same as the initial function, so the given series must be the representation of exponential of x. We try another series. Sigma of 3 to the power of k plus 1 divided by 2k factorial multiplied by x minus 4 to the power of k. Differentiating term by term of this series gives sigma of 3 to the power of k plus 1 divided by 2k factorial multiplied by k multiplied by x minus 4 to the power of k minus 1. The integration can also be carried out term by term, and the result is 3 to the power of k plus 1 divided by 2k factorial multiplied by 1 divided by k plus 1 multiplied by x minus 4 to the power of k plus 1 plus c. This is the end of section 8.7. Thanks for watching.